Thank you, Paul, and thank you everyone for joining this seminar. Do you see my screen?
Yes, we can see your screen, thank you.
Perfect, thank you. So yeah, as Paul briefly mentioned today, I'm going to present you this piece of research, which is regarding floating photovoltaics in the long-term energy planning of Eastern Nile Basin countries, and especially including in this study topics that are not traditionally considered in energy planning, such as water conservation, land use, and carbon emissions. So my name is Alessandro Pieruzzi. I'm a former student of TU Delft University in the Department of Water Management, and we conducted this piece of research together with my former professor, Ido Abraham. So this is the outline of the presentation I'm going to show you today. First of all, I'm going to give you a quick introduction on the motivation and study area that we chose for this study. Then we're going to deep dive into methodology, describing the energy planning framework that we took into account, and the environmental footprint accounting schemes that we developed, and as well the scenario analysis that we set up to test the model under different conditions. Then we're going to move to results and discussions, and finally to the conclusions. So we started this research with the question of studying and exploring the role that floating photovoltaics or FPVs might have in energy planning frameworks. And we analyzed the literature and realized that there was a gap regarding long-term planning studies, and especially covering large-scale energy systems. While most of the studies were focusing on techno-economic feasibilities of single sites and operational optimizations. So we narrowed down our research to large-scale energy systems, especially characterized by large reservoirs and hydropower networks. And this is because the literature suggested that this technology, floating photovoltaics, might offer unique co-benefits in these particular settings, such as reduction of evaporation losses, the leveraging of existing infrastructures, so the already existing hydropower dams, the reduction of land use competition with other sectors, for example, irrigation districts, and the stabilization of hydro-solar power outputs thanks to the complementarity of the generation profiles of these two technologies. Based on this, we identified the Eastern Nile Basin to be quite an interesting area, so covering Egypt, Ethiopia, Sudan, and South Sudan. Since this area, especially the last three countries, are characterized by low electricity access, but at the same time, the whole region is projected to undergo a sharp electricity demand increase over the next century. At the same time, this energy system is characterized by emission-intensive technologies, so it's dominated by fossil fuels at the moment, and there are interesting external drivers such as water scarcity and food security needs that, in our view, needed to be taken into account in a long-term energy planning study. So we decided also to integrate this environmental footprint in our study, as I was mentioning before in the outline. So given this context, we defined our research question to be to identify the role of floating solar power in satisfying this electricity demand increase in a sustainable way, and also to understand how the role of this technology could change under different climate change and socio-economic scenarios. So to answer these two questions, we defined our methodology framework, as you see in this graph. It's a bit complicated, but I will just quickly describe it. We had to first define a energy planning tool, and for this we chose Osmosis Temba, which is an open source cost minimization tool that in this version was developed especially for African countries. So it comes with all the techno-economic parameters that are needed to simulate the energy system. And we adapted these to the Eastern Nile Basin, so we removed all the countries that were not falling in our research area, and we adapted and updated some parameters. Then we had to introduce floating solar as a new technology, since this was not present in the original dataset. So we researched capacity factors and other parameters to add this technology in the simulation. Then we developed and expanded the footprint accounting modules that were in the tool, because the tool was coming originally with an emission accounting scheme. So we reused this, and we also created a new land use accounting module that I'm going to present in the next slides, as well as an evaporation assessment tool that is not integrated in the main model, but it is coming downstream, as you see here in this green box. So it's taking as input the outputs from the main model. And finally, we defined the scenarios that you see here in the blue boxes. So for climate change scenarios, I'm going to also go in more details of this in the next slides, and 2 taxation policy scenarios on carbon and land use to simulate the introduction of environmental footprints in the cost optimization. So a bit more on the model structure. So Osmosis, as I said before, is an open source cost optimization tool. So the objective of the model is satisfying the electricity demand, minimizing the cost of generation and capacity expansion. So the inputs are, of course, the electricity demands for all the 4 countries, the generation technology parameters for all generation technologies, and the cross-border electricity trade links between these countries. As outputs, the model returns capacity and generation mix, as well as the resulting CO2 emissions and land use that are relative to these optimal mixes. Regarding temporal and spatial resolutions, we defined 8 time slices, so 2-day parts to represent night and day over 4 seasons. And in terms of spatial resolution, we have the country level for most generation technologies, apart from hydropower and floating solar that we disaggregated at the single hydropower plant resolution to be able to better represent the hydropower network. Here on the right side of the slides, we have more information on the footprint accounting. So as I said before, the emissions were originally coming from the model we used, so Osmosis Temba, while the land use was developed by us by taking land use intensity per technology from this paper that you see cited on screen. And you see the values of land use in hectares per terawatt hours of generation in this table here. So we see that solar has a very high land footprint, while other technologies like geothermal, wind, gas, and nuclear have smaller land footprints. In order to be able to add a taxation policy on the land use, we had to define somehow a land value. And for this, we adopted as proxy the potential agricultural yield value of the region. And for this, we used an FAO dataset that we overlaid with a dataset containing all the power plants of the regions. So we did a statistical analysis between these 2 datasets and obtained statistical land values for each generation technology. Finally, regarding the evaporation reduction, our module takes the optimal capacity of floating solar panels obtained by osmosis, and then converts this to a coverage surface area with a conversion factor from the literature. Once we have this coverage area, we divide it by the total reservoir surface to obtain a coverage percentage. Then this coverage percentage is translated into an evaporation reduction percentage using curves from another floating solar panel studies from the literature. And finally, we multiply this reduction percentage by the annual evaporation rate to obtain the yearly water savings for each reservoir. Then, regarding the scenarios, we defined 4 or 5 types of scenario groups. The first one is the baseline scenario that allows us to define how the system behaves under business as usual assumptions. So there is no introduction of floating solar, no climate change, and the expansion happens under current policies. Then we have the same scenario with the introduction of floating solar. So it's a reference floating solar panel scenario, the second one here. And this, the only difference with the previous one is indeed the introduction of this new technology. So this allows us to see how the mix changes and how the footprints change when we introduce this technology. Then we have the climate change scenarios, where we simulate the system under two combinations of SSP, RCP scenarios, and under two cases of hydrological regimes. So one dry case where we consider the 5th percent of hydrological flows, and the wet case where we consider 95th percentile of hydrological flows. So to simulate this into our energy system, we took altered capacity factors under these scenarios that were developed by another author in a previous paper, and we plugged them in our electricity simulation model to see the effects of these altered hydrological flows. Then we simulated two scenarios with the introduction of taxation policies. And the two taxation policies we introduced are one on emissions. So we added a carbon tax on every ton of CO2 that generates from each electricity generation technology. And then we added a land use tax. So as I was explaining previously, adding a land value for each technology and multiplying this by the land use of each technology in hectares per terawatt hours. And we simulated the introduction of both these taxes together in a lower form, so in the tax low scenario, and in a higher form in the tax high scenario. And then we also simulated the introduction of these policies singularly. So first the carbon tax in their low version, in their high version, and same for the land tax in both versions. So we have a total of 12 simulation sets. And yes. So in terms of results, I wanted to show you first the electricity generation over the whole scenario, which is from 2023 to 2065. And here we see the generation in petajoules per year. So each bar represents 1 year. And we see that the mix is still mostly dominated by fossil fuels in the reference scenario, but there is also a extensive expansion of solar and wind generation. It's also interesting to notice that the hydropower generation slightly reduces over the horizon, and there is also constant export of electricity to neighboring countries. Then, when we introduce floating solar, to better see exactly what happens to the mix, we plotted here a differential graph. So it's the same concept as the previous graph, but this is the difference between the reference scenario and the reference scenario with floating solar panels. So the positive bars here represent the generation that is added when we introduce FPVs in the mix, and the negative part represents the generation that is replaced. So we see here that floating solar, which is the green bars, have an early onset in the mix. So they are cost optimal already from the late 2020s. And they arrive to generate up to 3% of the mix at full capacity. We see that they replace solar generation, but also some gas and coal generation, and some wind generation in the last part of the simulation horizon. And it's also interesting to notice here how hydropower generation, these light blue bars, increase with the introduction of floating solar. And this is due to this complementarity between capacity factors. So it is indeed, for our model, more cost optimal to generate together floating solar panel and hydropower rather than other technology mixes. In terms of environmental footprints, you see here the effects of introducing solar panels in the mix. So we have a reduction of emissions of 66 megatons, a reduction of land use of 150,000 hectares, and a reduction of water evaporation by 300 76 million of cubic meters. These numbers in absolute terms might look quite relevant. If we look at the relative reductions, these are more contained. We have 0.4 regarding emissions, 0.8 regarding land use, and 2% regarding evaporation. But we need to take into account that our simulation is running over 40 years of horizon and over a regional power grid. So these reductions in the large scale setting are diluted. But of course, if we consider smaller spatial resolutions, they might be much more relevant, especially land use and water savings, if we consider competition with other sectors such as agriculture and similar. So finally, regarding the results for the scenario analysis, I reported here a table of maximum floating solar panel generation and a graph of capacity expansion. So in terms of maximum generation, we see that the climate change scenarios have a small effect on the generation from floating solar panels that go from 2.98 in the reference scenario down to 2.78 in the RCP 2.6 wet scenario. But if we look at the capacity expansion in the graph, we see that the wet scenarios slightly delay the capacity expansion of floating solar because hydropower profiles are increased due to the wet regimes, while in the dry case, the effects are smaller, with the line being very close to the reference scenario, which is the pink line. The taxation scenarios instead have a slightly bigger effect on generations that reach 4.46% in the high case. And we also see that the capacity expansion is anticipated in both versions of the taxes, so in both high and low cases, and hence the generation over the whole planning horizon is increased. So I wanted to stop here 1 second to discuss the contribution and limitations of this work. So first of all, we integrated the floating solar into a long-term energy planning for this region in the Eastern Nile Basin. We introduced this land use cost methodology. We disaggregated the floating solars at a single site resolution, and we took into account multidimensional topics such as emissions, land use, and water savings, and tested everything under different policy and climate change scenarios. In terms of limitations, climate change here is only captured through variation of hydropower capacity factors, so we don't take into account solar and wind variability nor demand shifts. The evaporation model is robust but rather simplified and relying on a set of assumptions. And the demand projections are at the country level without further subnational granularity. And finally, the land value is using a proxy as agricultural yields, but is not capturing other potential competition from other sectors. So in terms of future research, we suggest a refinement and update of the parameters and assumptions, including a finer spatial resolution for all the technologies, and to include and develop more studies on local analysis, for example, between the introduction of this technology together with land use and evaporation savings studies at a smaller spatial and temporal scales. So yeah, thank you for your attention.